video I'll be showing you how I solve gas law problems. So just for the purposes of this video, I'll be using the questions that Mr. Porter has given us for the first test. But typically what I do is that I write out a balanced chemical equation, I write out my givens and I convert them to the proper units, and then I use the mole ratios to examine the element or compound that we're looking for. And then you use the ideal gas law to solve for information about some element or compound. So that's like a pretty standard way of solving gas law problems. So I'll just be going over some of the gas law practice questions that we were given. So the first question is, what volume of gas will be produced at 22 degrees Celsius and 101 kilopascals when 5 grams of zinc is placed in 500 milliliters of 0.200 mole per decimeter cubed hydrochloric solution? So I start by writing out the givens. I convert them into the units that I need. I write a balanced chemical equation. In this case, it's going to be a single displacement equation. And then I balance it. So this is a balanced chemical equation. We use this for the mole ratios. And we're given some information about the zinc. We're given that the mass of it is going to be 5.00 grams. We could find the molar mass by looking on the periodic table. In this case, it's 65.39. Then we can plug this into our calculator. And give 3 sig figs, but 1 extra because it's an intermediate calculation. And then we want to find the number of moles of hydrogen that are produced. Look at the coefficients, there's implied 1s, so that means it's going to be the same number of moles as the number of moles of zinc. Then we want to look at the number of moles of hydrochloric acid. So the concentration is 0.200 mole per liter, and the volume is 0.5 liters, or 500 milliliters. We plug this into our calculator, and we get 0.1000 moles. Looking at the number of moles of hydrogen, it's a 1:2 ratio. It's going to be half. And we want to take the smaller value because the Zn is going to be limiting the completion of the reaction. So this is going to be the number of moles of hydrogen. Now to find the volume of hydrogen, we want to rearrange this equation for volume. And then we want to plug in the values that we have. And we want to solve it to the number of sig figs that we were given. So we're given the mass was 5.00 grams of zinc, so we want 3 sig figs. And so our answer comes out to 1.21 liters, or 1.21 decimeters cubed. So we can apply a similar thinking process to solving the second question. A butane lighter contains 2.56 grams of butane, or C4H10, If all the butane is completely combusted, what is the total volume of gas produced at 351 degrees Celsius and 100 kilopascals? So we want to start out by writing a complete combustion equation. So we have C4H10, which is a gas, reacting with O2, which is a gas, and it's going to yield H2O and CO2. CO2 we know is for sure a gas, and at 351 degrees Celsius, water is going to be a gas. Now let's see if this is balanced. Typically in combustion reactions, there's always going to be a 2 in front of the hydrocarbon. So we have a 2 here, we're going to have an 8 here, and then we have 20 hydrogens, so we need 20 here. So we have 10 plus 16, so 26. 26 oxygens, so we need a 13 here. Now, since we have a balanced chemical equation, we can look at the other information that we're given in the question. So we're given the mass of butane. This immediately means we have to find the number of moles, since we're given the molar mass. So that is the only thing to solve for. Number of moles of C4H10 is 2.56 grams, divided by the molar mass. The molar mass is 4 times 12.011 plus 10 times 1.0079 units. It's going to be 58.123 grams per mole. And now we want to give 4 sig figs since it's an intermediate calculation. So it's 0.04404 moles. And we want to find the number of moles of gas. So these are both in a gaseous state. So this is going to be, so if you want to find number of moles of gas, we're going to have 0.04404 moles times 18 moles of gas divided by 2 moles of C4H10. So times 9. So we're given 0.3964 moles. Now what do we want to find? We want to find the total volume of gas. So if PV equals nRT, rearrange for V, volume of gas equals nRT over P, 0.3964 moles times 8.314 kilopascal liters per mole Kelvin times the temperature. Temperature is 351 degrees Celsius. So we add 273, 351 plus 273 equals 624 Kelvin. And we're also given the pressure, which also happens to be in kilopascals. So it's 10, just 100 kilopascals. So temperature is 624 Kelvin. And then we divide by the pressure. And ultimately we need, we need 3 sig figs. 0.3964 times 8.314 times 624 divided by 100. It's going to be 20.6 liters. Moving on to question 3. Again, it's going to be very similar. So, if 0.085 grams of magnesium is held in a hydrochloric acid solution, what volume of gas will be collected over the solution once the reaction is complete? Assume the temperature is 20 degrees Celsius and 101 kilopascals. In this type of experiment, the gas is collected in a long tube, sealed at one end, initially filled with water. Water has a vapor pressure of 2.34 kilopascals at 20 degrees Celsius, which is the temperature that we're given. The gas produced bubbles to the top of the tube and pushes the water out. There are no measuring instruments in the tube aside from a scale to indicate the volume. What steps would you take to ensure that the gas inside is actually at a particular temperature and pressure? So this is more of a theoretical question. So I'll mainly just be addressing the computational aspect of this. And so we're given that magnesium is going to be reacting with hydrochloric acid. So we typically want to start out by writing a balanced chemical equation. Okay, so let's see if this is balanced. So we need a 2 here. And we want to find the volume of gas. So that's just going to be the hydrogen. Again, we start with a mass, which is 0.085 grams. So we want to find the moles of magnesium first. So the molar mass of magnesium, we'll be looking at our periodic table. It's going to be 24.305. If you do these often enough, eventually these numbers will just stick in your head, no matter how many there are. So we want to have 3 sig figs, since it's an intermediate calculation. And of course, we want to have 2 in the end. So it's going to be 350. And so we have the number of moles of magnesium, so the number of moles of hydrogen is going to be the same, since the coefficients are the same. So now, next we're given that the temperature is 20 degrees Celsius, and adding 273, that's going to give 293 kelvins. And then we're given the pressure is 101 kilopascals, except we're also given that there's a vapor pressure at 20 degrees Celsius, meaning that the pressure of the atmosphere equals the pressure of the gas plus the pressure of the water. So in order to account for the actual pressure of the pressure of the water, we have to subtract pressure of the water from the pressure of the atmosphere. Pressure of the atmosphere is 101 kilopascals. Pressure of the water is 2.34 kilopascals at 20 degrees Celsius. And so the pressure we'll actually be using, which is the pressure of the gas, is going to be 98.66 kilopascals. And so now we can pull out the PV equals nRT equation. What are we trying to find? Trying to find the volume? Yes, volume. So volume equals nRT over P. This is typically the form of the equation that we'll use for gas laws, as we're given the temperature and pressure often. And now we just want to plug in the information that we have. And now we want to simplify to 2 significant digits. And so our answer will be 0.086 liters. Moving on to the 4th question. In a related experiment, 67.4, I like how it always defaults to a pretty ridiculous, oh, I suppose this is a drawing tool, so I guess that makes sense. So 67.4 milliliters of gas is collected over water in a gas measuring tube. Temperature of the water is 20 degrees Celsius. The atmospheric pressure is 99.7 kilopascals. How many moles of gas were produced? So in this case, we're already given that the vapor pressure at 20 degrees Celsius is 2.34 kilopascals. And so the first thing we want to do is we want to find the actual pressure of the gas, which is going to be equal to the atmospheric pressure minus the vapor pressure. And this is going to give us, plugging it into my calculator, 97.36. And then what are we trying to find? We're trying to find the number of moles. So the number of moles is going to equal the pressure times the volume divided by the constant and the temperature. So pressure, we have the volume is 67.4 divided by 1000, which is 0.0674 liters, divided by the constant, and temperature. This is going to give us so we need 2 sig figs, I believe. Okay, no, we need 3 sig figs. And that will be all for this video.